So, title of this talk is Reactive Java EE, Let Me Count the Ways. My name is Reza Rahman. I'm a Java EE evangelist at Oracle Corporation. Up there is my email address and Twitter handle. If you need to reach out to me afterwards, please do. And that's always welcome. Even if it's 6 months from now, perfectly happy to answer any questions that you may have. A little bit about this talk before we get too far into this. I actually got this the idea for this talk from somebody at a conference. So I went to a conference called a Scandinavian conference called oh my gosh, JFocus. And then somebody in the audience came up to me and said, well, have you heard of this thing called Reactive? And I said, yeah, I've heard of this thing called Reactive. All those Scala and Akka guys keep talking about it, and it's the latest hipster thing. I kind of know what it is. And he basically told me, well, maybe not so, because he said, I think that you can actually design pretty reactive systems using nothing much more than vanilla Java SE and vanilla Java EE. So I said, interesting. Let's talk about that. So I scheduled sort of a little coffee meeting with him afterward, and I listened to what it is that he had to say. And in fact, he was right. You can design very reactive systems using nothing much more than just vanilla Java EE and Java SE, specifically Java EE7 and Java SE8. So that is basically what this talk is about, is to show you why that statement may actually be very true. So before we get started, the other thing I need to kind of get out of the way is the safe harbor thing that they make Oracle employees show you. So the reason this is there is because I may be talking a bit about what we may or may not be doing in Java E8. So that portion kind of take with a grain of salt. That may change in the future. But by and large, everything that I will tell you today is current state. I will mostly be talking about Java EE7 and Java SE8. Okay, so before we get too far into this, the most important thing that we should understand is exactly what is reactive programming and why you should take it seriously, or maybe why you shouldn't. So believe it or not, this term reactive is actually fairly old. This term first appeared sometime in the late 80s or so. And generally speaking, it is a relatively straightforward concept. So here's how I would explain it. It is basically making a change in one part of your application and the effect of that change showing up somewhere else. So a good example, simple example of this is Excel spreadsheets. So let's say you have an Excel spreadsheet and you have a cell that is dependent upon another cell because of a dependent function call. So when you make a change to that cell that is the originator, and that change automatically propagates to the other cell and affects a change there. So that is basically what reactive programming, the core principles of reactive programming is about, the original definition of it. Since then, the term reactive has sort of gone through some evolutions, and more recently, as I said, with Akka and Scala and Actor folks. Unfortunately, this remains a very, very confused term. And that I don't think is very good for the average Java developer to adopt this concept. However, so because of that reason, what I will first attempt to do is explain to you what my interpretation of what the core principles of reactive programming really is. What exactly is it that makes reactive programming uniquely valuable? So in my view, if you are thinking about one or more of these concepts that I have listed here, you are essentially talking about reactive programming. So these concepts are event-driven, asynchronous, non-blocking, and message-driven. So what is event-driven? Well, event-driven is very similar to that concept of the Excel spreadsheets. A state change occurs in your system that triggers an event. The event will trigger some reaction in your system. Asynchronous is simply doing things outside of your current thread. Okay, so whatever your current thread of execution is, you're going to do something outside of that current thread, and that is what asynchronous programming was all about. Non-blocking is essentially about trying not to block your thread of execution as much as possible. Okay, so you will try to make sure that your thread is never simply halting and waiting for some input. That is what non-blocking is about. And generally, message-driven is synonymous to event-driven. Okay, so a message arrives at your system, and you have to react to it in some way. So beyond these core principles, though, there have been a few other overloaded concerns that have been introduced with reactive programming. So let's explore some of these ideas and talk about why they're not necessarily important in understanding the core value proposition of reactive programming, especially in terms of Java EE in particular. So some of these words are things like responsive. I'll talk about responsive in a second. I won't quite explain it right now. I actually think that responsive is a motivation for doing reactive rather than a characteristic of reactive programming per se. Resilient or fault tolerant, that simply means that when a error occurs in your system does not come crashing down and halting. Okay, so your system can recover from a fault or an error. Elastic or adaptive, that simply means that resources in your system can contract and expand in response to contracting and expanding demand. Okay, so in Java EE terms, things like fault tolerance are built into the Java EE implementations through things like clustering and load balancing and failover and the like. Same thing with elastic and adaptive. So these are concepts like pooling or elastic scaling of clusters. Again, Java EE application servers generally deal with these concerns, not at the API level, but at the infrastructure or runtime level. So you, as a developer, can take most of these things essentially for granted. You just need to deal with the APIs, and the runtime deals with these particular characteristics of your system. Same thing with scalable, right? Scalable simply means that when system load increases, your entire system doesn't simply collapse. Your system can continue producing throughput. Again, Java EE does a whole bunch of things, so things like resource pooling, for example, caching, load balancing, to make sure that your systems, again, are scalable. So clearly, these are important concepts, right? If they weren't important concepts, then vendors wouldn't go about implementing these and baking them into their platform. However, the important thing that you should realize is that these things are important regardless or whether you're dealing with a reactive system or not, okay? Whether or not you're dealing with events, whether or not you're dealing with asynchronous programming, as long as you have an enterprise system, you will need to deal with these concerns. So in fact, these concerns are not specific to reactive programming. And also, in fact, most of these concerns are met by Java EE runtimes, not at the API level, but at the runtime level. So for our purposes, for the purposes of our discussions, we can largely ignore these and focus on what really makes reactive reactive. What is it that makes reactive important? Okay, so the other thing we should understand is, well, we sort of understand what reactive programming is. So why is it that we're talking about it today? Well, why is it so important? Well, first and foremost, notice that I told you that these are old ideas. So because they are old ideas, they actually solve relatively well-known problems. So first and foremost, what you want is a responsive user experience. Okay, you want a system that at least appears to respond to user input. And one way you can do that is by using event-driven programming or asynchronous programming. So a good example of this is the spinning wheel that you get when you do something, run a lengthy operation in Windows. So what is happening there is that the UI thread is showing you the spinning wheel, and the actual work is actually taking place on a separate thread. So that is an example of reactive programming. By and large, having a system that can handle throughput at a higher frequency is again goes towards designing responsive systems. So these again are important intrinsic concerns of reactive programming. Reactive programming also helps you achieve high throughput by making optimal use of hardware and CPU. Well, how does it do that? So what you are doing with things like multi-threading, using multiple threads in asynchronous fashion, and also using non-blocking threads, so making sure those threads that you're spawning asynchronously do not block. In the end, what this happens is this makes you use CPU much more, so much higher CPU usage and also higher throughput. Right, so this is again intrinsic to why reactive programming is important in the end. And finally, there are some systems that are inherently event-driven. Okay, so these are loosely coupled, complex event-driven processing systems. So one good example of that from my own career is things like stock trading. So a stock trading engine is actually a very good example of a reactive system. Why is this? Well, when you are talking about a stock processing backend, it actually does not have a UI per se. Okay, the UI is many different things, and it receives inputs in terms of stock exchanges from all of these different remote places in the form of events or messages. And then it reacts to those messages and says, okay, this particular stock change affects this change in the market. Okay, it's a large state machine, if you will. And then finally, it sends out events to people that need to know about this state change. So it's an event input and output system. Again, very good, nice, natural fit for reactive programming. So is there anything that is happening in our industry today that makes reactive programming more important? Well, in fact, yes, there are. There are several different things going on. One is this thing called IoT, or Internet of Things, essentially device-to-device communication. So today we use the internet mostly by humans. So it's human-to-machine interaction. Well, the nice thing about human-to-machine interaction is that we humans are relatively slow. Okay, so that means that although it is challenging to scale a system when you have many users, it is not as challenging when you are dealing with machine-to-machine communication, because a machine is going to communicate at a much higher frequency with another machine. So that increases overall system load, which again makes reactive programming a valuable technique. Also, if you look at analysts out there, they will tell you things like, oh, we suddenly have a lot of mobile devices connecting to your system. You suddenly have a global user base that's much larger than the local user base that you may have had in the past. You may have more chatty applications because all of these mobile applications and things like HTML5 applications are very, very chatty. They communicate much more frequently with your backend. So again, all of these things, if they indeed turn out to be valid trends, also increases overall system load, which again makes reactive programming a valuable technique to have in your tool belt. However, the thing that I want you to also understand is that I'm not in the business of telling you reactive programming is end-all, be-all, and it is the cure for all of your ills. It is not. So one thing that it will be relatively clear to you is that asynchronous event-driven code is almost always more complicated and harder to maintain and write than synchronous blocking traditional code. So think about your CRUD application that is a simple, perhaps an interface for your database. Okay, that's a simple code to write in comparison to the asynchronous style and event-driven style of programming. In the end, also understand that API programming is only one solution to the problem. The other perfectly valid solution to any scalability problem is also simply adding hardware, either horizontal scalability or vertical scalability for a given machine. And in fact, this may be the right answer for you. Okay, so it is a matter of a judgment call, whether you simply solve scalability problems by not by having simple systems that use a lot of hardware, or having complex systems that potentially use lesser hardware. However, in the end, what I also want to tell you is that if you truly have a reactive problem, scaling through hardware alone may not be an option. Okay, the requirements of hardware may simply be too great, in which case you really do not have an option other than to use reactive programming. Okay, so as I said, the nice thing about it is Java EE actually provides you quite a bit in terms of what you can use for reactive programming principles. So these are the kind of things that are there. Okay, so you have JMS, EJB3, message event beans and asynchronous session beans, CDI events and observers, servlet support for asynchronous and IO programming. JAX-RS provides async both on the client and the server. You have WebSocket remote endpoints, and finally, we've also added a new API called the concurrency utilities for Java EE. This was added as of Java EE 7. As you can see, quite a bit of ground to cover. So my goal today is not necessarily to do a deep dive of any of these technologies. What I want to do is a brief tour of all of these technologies so I can introduce them to you and explain how they fit in the overall picture of reactive programming. All right. So we shall start our tour with JMS. JMS is actually a very, very old API. JMS has been around since the J2EE days. And in fact, JMS is a very, very natural fit for the problem of reactive programming. This is because at the end of the day, JMS is nothing much more than a Java API for message-oriented middleware. And message-oriented middleware essentially is designed to solve the problem of event-driven programming, message-driven programming, and asynchronous programming. Okay, so it's a very natural fit. Out of JMS and its implementations, you get things like loosely coupled systems. Okay, when you're dealing with JMS, you get reliability, you get transactionality, durability, fault tolerance, error tolerance, clustering, load balancing, pooling, all the like. Okay, all of the things that are important for reactive programming principles beyond simple programming paradigm of message or event-driven programming and asynchronous programming. On the receive side of the messages, you have another very powerful tool called message or driven beans. Okay, in Java E7, these are really nothing much more than simple POJOs with annotations. If you haven't seen that before, I will show it to you in the subsequent slide. Again, by virtue of JMS, you get a whole bunch of those nice reactive features that helps you build robust asynchronous systems. Again, things like transactions, thread safety, pooling, reliability, load balancing, fault tolerance, error tolerance, and the like. Okay, all simply delivered to you as POJOs and annotations. So extremely powerful programming model that you should not underestimate. Here's a simple example of JMS 2.0. If you have not seen this before, this is how JMS 2.0 code looks like. In this code, we are doing something relatively simple and very intrinsic to firing events. Okay, we are sending a POJO event to a JMS destination in this code example. Notice how compact and powerful this code is. Okay, so you are sending the message payload, but you are also doing a lot more. You're actually setting quality of service parameters. You are setting the delivery mode to persistent, a priority to be low. These other two calls may not be familiar to you if you're not familiar with JMS 2.0. These are two message level optimizations. So in this case, I am disabling both the message ID and the message timestamp because I do not need them in this case. I'm also setting a custom string property called source. Okay, and I'm doing that in a single line. Okay, just a single line, a Fluent API, and if you, this is just the tip of the iceberg. This is a very, very powerful programming style that lets you do simple things very simply and extremely complex things still possible. So if you have not explored JMS 2.0, you should do so. On the receipt side, as I said, it's a simple POJO with annotations. Okay, so this is nothing much more than something that is receiving the message that I sent. Okay, so I'm simply unwrapping the message, and I'm going to handle this message in my code. How do I receive it? Well, it's very, very simple. I simply annotate it and provide some metadata like what JMS queue am I listening to. In addition to that, I'm also applying a filter using a message selector. So I'm saying that I only want to receive events from a mobile source. Okay, so very, very powerful mechanism. And indeed, there's a lot more other things going on here. So for example, although it's not visible to you right away, the on-message delivery is actually automatically transactional. Okay, that means that any changes you make on the on-message method is synchronized through a transaction with the message delivery itself. If you fail in this method, that message will be redelivered for you automatically. Similarly, there's acknowledgements going on here as well behind the scenes, without you knowing anything about it. Redelivery, as I said, also also error handling. If you throw in runtime exception here, this message will be sent back to the queue and redelivered to you at a later point in time, all in a clustered and load balanced fashion. So this gives you a very strong foundation and a very strong backbone of writing message-driven systems using Java EE. Next stop in our tour is asynchronous session beans. Believe it or not, if you could imagine the simplest possible solution for asynchronous programming, this is it. Okay, as I will show you in the code examples, it's a simple matter of placing an annotation on a POJO method to get asynchronous behavior. It's a very, very simple mechanism. It's very, very good when all you really need is greater throughput or responsiveness by putting a task on a separate thread. Okay, so it is still transactional. It is still thread pool. It is still thread safe and still pooled. However, unlike JMS, in this particular case, it will not be loosely coupled. You will not get persistence, which means if you have failure in the middle of your asynchronous method invocation, that message is lost. Okay, unlike in JMS, where that message will not be lost. Generally, it is also not fault tolerant or error tolerant either. Okay, and it is also not clustered by and large. So these are things you will have to handle yourself. If you care about them, or you can use JMS instead of asynchronous asynchronous session beans. You can think of asynchronous session beans as essentially messaging light or asynchronous programming light. So how do you do it? In a very simple case, let's say I am processing a payment. This payment may be processed, may take a lot of CPU or I/O. And I don't want the user to sit around and wait for this payment to be processed. Well, I can simply put this on a background thread by annotating the process payment method with @asynchronous. That is all you need to do in the end. You can then inject this EJB and invoke this all as though it was a normal blocking call. Yet this will be put on a separate background thread for you automatically. In a more complicated case, let's say that we actually do want a return type back. Okay, so in the first case, it's simply fire and forget. In the second case, we are actually expecting a report back. Okay, so we are generating a report. Again, potentially a CPU heavy or IO heavy task that we want to create asynchronously, and hence we are placing the @asynchronous annotation on it. Now the question is, well, how do you get this return type back? Well, it's a very, very simple programming paradigm, because what you can do is you have a return type of future with the type of data that you want, in this case a report. And the handling of it is still very simple. You still write your asynchronous code as though it's a normal synchronous blocking code. The only difference is when you want to return a result, all you really need to do is wrap it with this async result wrapper. Okay, and that's it. And whether you're sending back an exception or sending back the result of normal execution is still exactly the same programming paradigm. So if you really think about it, this is as simple as you can get in terms of how you can do asynchronous programming. Again, a very, very powerful feature that Java EE gives you. How do you do this on the client side? A simple example here. So again, you're receiving the report as a Java util feature object, and then you get all of the facilities that Java util feature gives you. So in this case, you can check to see when this asynchronous processing is done, and perhaps you have this inside of a wait loop where you're doing something else. Okay, in parallel as well, or maybe just showing the spinning wheel to the user. Okay, that's where you would do that. And you can also do things like when the result is done, do a get to actually get the results of asynchronous processing, and even also do a cancellation, okay, of the asynchronous process. EJB will handle this for you. Okay, there's an example of that. So again, a relatively powerful mechanism. As powerful as this is, there are some limitations to this, specifically the Java util feature object. We'll talk about that towards the end of the presentation if we have time. Okay. Next up in our tour is CDI events and observers. Okay. CDI events and observers are useful when the problem that you're trying to solve is loose coupling. That's it. You only care about loose coupling via events and maybe a little bit of filtering and chaining. But other than that, you don't care about the rest. So you don't care about asynchrony, for example. Okay, if you don't care about asynchrony, then CDI events and observers are fine. Okay, it's a simple mechanism for, again, decoupling events in your system. In CDI2, this may change. In CDI2, they are looking into making CDI events actually asynchronous. Okay, so that potentially may change as well. But other than that, it's a simple, elegant, and type-safe way of handling events in your system. Okay, you can basically think about it as the observer, the gang of 4 observer pattern, formalized inside of a DI framework nicely with some annotations. It becomes clearer when you take a look at a simple example. So in this example, I want to be notified when a cargo is inspected. Okay, the cargo is actually the domain object, the object that the data encapsulation object that I'm interested in. So where I need to fire an event notifying everyone that I've inspected the cargo, I simply call cargo inspected.fire. Okay, the cargo inspected object is nothing much more than a CDI event object with the payload of cargo, and you simply inject it the same way as you do here using the @inject annotation. In addition to that, you can actually apply CDI qualifiers to add additional metadata. So in this case, I'm saying that, well, I'm firing a cargo event, but this particular event really should only be captured by folks that are interested in when the cargo is being inspected. Okay, so that's why I have a custom CDI qualifier down below. In terms of receiving the event, it's a very, very simple programming model. Okay, so again, it's just a POJO method, all right? The payload is cargo, the type of data object that I want to receive, and simply the observes annotation. Okay, the observes annotation will make sure that whenever a cargo event is fired, that it will be delivered to this method for you. And you're also saying that, okay, in this case, I'm only interested in the cargo when cargo inspected qualifier is present. Okay, so this again gives you some filtering and chaining capabilities as well. So again, a very, very simple mechanism to do event-based programming using Java EE and CDI. Okay. Next up in our tour is the very, very old and mature servlet API. Having proper reactive programming support at this layer is actually very, very important because this is the foundational layer for many other APIs. Okay, and you'll see one of those APIs, namely JAX-RS. Fortunately, we have both support for asynchrony and NIO in this layer. Okay, and we'll see how this is and what this is. The best way to understand this is actually through code examples. So let's go ahead and dive into a code example of an asynchronous servlet. Okay. So in order for a servlet to be asynchronous, you actually need to mark it with the async supported true metadata. Okay, and that puts this servlet in a special type of mode. And we'll see what that mode is and why that's important. This async servlet actually underneath the hood behaves very differently compared to just a synchronous blocking servlet. So why is it that I'm doing this? As you can see in my doGet method, I am doing something potentially time-consuming. So it's that report generation task again. Okay, so because it could be a potentially long-running task, I want to process this in an asynchronous fashion. Okay, so that is where the async context comes in. All right, so let's think about this for 1 second. When you I want you to take a look at this code real quick. So first thing you need to do in order to get an async context is invoke request.startAsync. Okay, and I'll explain to you exactly what the async context does in just a second. Okay, after I explain the next line of code to you. So in this next line of code, what I am doing is saying async context.start. Okay, this is a convenience method. What this method does under the hood is that it starts a new thread altogether, a new thread of execution. Okay, in the background. So looking at this code, the servlet doGet method is going to return immediately upon hitting that's async context.start method call. Correct? So in our normal servlet execution environment, as soon as the doGet method returns, the connection is automatically closed. All right? So you do not want that to happen in this case. All right, because you are still going to use the connection. You're not even done yet. You haven't read the data that you need or wrote out the data that you need, okay, that you're now processing on a separate thread. So what the asynchronous context actually does is that it makes sure that the connection is alive and kept alive even though this doGet method will return. All right, so that is a handle to that passivated session that's stored for you behind the scenes. Now, looking at this block of code, you'll see this funny arrow expression. Okay, well, what's that? That is, if you have not seen that before, essentially a lambda expression. Okay, a lambda expression is nothing much more than creating a block of code that's wrapped up as though it's an object. Okay, in this case, the lambda under the hood is actually creating a runnable object, so you don't need to create an anonymous inner class anymore. Okay, that class will automatically be created for you as long as you use this lambda syntax. So this is actually very, very helpful for our reactive programming code, as we will see as we go through. In the rest of this code, what I'm doing here is getting the request parameters, okay? Again, using the async context handle that I have, okay? So this is on a separate thread. I'm in a background thread. The connection is still available for me, hence I can get the request back. And finally, when I'm done generating the report, I can actually print the report out. All right, so I can, in order to do that, again, I get the context, the underlying connection from the context by saying async context.get response, and that gives me the passivated response UI IO handle. And finally, when I'm done, I'm going to say async context.complete. And as soon as I do that, that is when the underlying connection is actually cleaned up and retrieved back. All right? So the other thing that I want to bring to your attention now is imagine for a second that this report is a large PDF report. So let's say it is perhaps a couple of 100 megabytes, okay? Now think about this. I'm going to write, in my print report method, I'm going to write out a couple of 100 megabytes over potentially a slow connection on the internet, okay? If I used normal IO to do this, what could potentially happen is that I may block, Okay, I may block on that IO thread because there is network latency on the internet connection from the client, between the client and the server. What that means is if I block, I'm actually going to block this thread, this valuable background thread, basically defeating the purpose of why I would want to create this thread in the first place. I'm no longer getting the throughput that I need. So is there a solution to this problem? And the answer is that, in fact, yes, there is a solution to this problem, because Servlet, in addition to simply giving you asynchronous capabilities, also gives you NIO capabilities. Okay, so this is how you do NIO. All right, NIO is very different from normal IO, and we'll see why that is in a second. It's doing IO in a non-blocking fashion. So the first thing I do here is, as you can imagine, get a handle to the response output stream. I need that. That's the one I'm going to write to. However, instead of writing normal code in doing print statements on the servlet output stream, what I'm doing instead is creating a write listener, my own write listener implementation. It is called report write listener. I'm giving it a few bits of data that I need. And then I am taking the output stream and setting the write listener, okay? Which means that this thread is actually going to return, okay, right away after I do this set write listener. So the question then is, well, where's the write? Okay, and the answer is the write happens in an asynchronous fashion. Okay, so before I can explain that, I'll just explain the simple implementation of a write listener. All I'm doing here is I have a constructor and a few fields. I need these bits of information. So I need the output stream. I need the actual input, okay, the actual PDF, and I need the async context. For my processing. The real magic of NIO actually happens in these two callback methods in my write listener. Okay. The first one is very, very simple. It's on error, the one that is below. All that happens here is I am, remember, attaching to an output stream. So if there is an error on that output stream, I will simply be notified you have an error. Okay. So in this case, if I have an error, all I really do is I say, oh, I don't know what this error is. I'm just going to context.complete, which is going to, again, clean up the servlet and clean up all of the connections associated with the servlet. More interesting is the on-write possible callback. Okay, so what happens here is that we get notified by the underlying IO stream when the IO stream thinks that it is ready to write. Okay, there is bandwidth available for you to write output to the stream. In this method, the other trick that we are applying is that we are not simply, as soon as we get a notification that write is ready, we're not simply blindly writing out the entire couple of hundred meg data. What we are doing instead, in order to avoid blocking, is writing data in small chunks instead. Okay, in my particular case, it's only 256 bytes at a time that I'm writing. And as you can see from the loop, I simply keep writing until I have something to read, right? As soon as I hit read equals -1, then I'm done. Okay, I'm finished. Then I can terminate this loop, and I can simply say context.complete. Okay, but other than that, I cannot. The other thing you should notice is the output.isReady in the while loop. Okay, so it's not like the on-write possible is once and done. It's not like I get the callback once and I am finished. That is not the case. What happens here is each time I do a write of 260 bytes, I have to check to make sure that I can write further. Okay, can I write more data? If I cannot, then I need to terminate this callback and then wait for the next callback when the IO stream tells me, hey, now you are ready to have more output. Okay. JAX-RS similarly has asynchronous capabilities as well. On the server side, the asynchronous capabilities in JAX-RS are very, very similar to the asynchronous capabilities built into servlet, actually. It just has a slightly nicer declarative syntax. There's also async capabilities on the client side. For those of you who don't know this, JAX-RS now has a client-side API as well. Okay, and the client-side API also has asynchronous capabilities built into it. There's two forms of asynchrony actually supported by the client API. Futures, which you have seen before, okay, from the EJB asynchronous code, as well as callbacks. However, there is no NIO support built into JAX-RS yet. Okay, so if you have large volumes of data that you need to write, unfortunately, you will still run into the blocking issues if you're using JAX-RS. Okay, but by and large, it's not an issue if you don't have large blocks of data to write. Okay. So how does it look like? As I said, it's a nicer declarative syntax, but it's very similar conceptually to the servlet asynchronous processing. Okay, so let's take a look at this code. Basically, I've taken the servlet example that you saw before and refactor it to use JAX-RS now. Okay, so and I've also removed all that manipulation of the thread and lambdas and all of that. So I don't need to use any of that. I just want to use my very nice EJB at asynchronous annotation. Okay, so this means that this generate report method, as soon as it hits that method, the client will receive a return right away. Okay, and I will actually execute the generate report method automatically on a separate background thread. Okay. Again, because I'm doing that, I need something to keep a handle to the underlying connection. Okay, and in this case, the handle is something equivalent to async context. It's called async response, and you can simply use injection. Okay, in a JAX-RS mapped method, you can just inject the async response, and then you can go about doing whatever it is that you're going to do, right, in the long-running thread. When you are done, you simply call response.resume, okay, and that will do the same thing as context.complete. It will send the data out, it will flush the buffers, and it will close that connection, okay, close the underlying connections for you. Okay. On the client side, this is how the API looks like. So we have, in a normal case, let's take a look at the code above. If you wanted to make this call, which is getting balance, okay, getting bank balance, this could potentially be a long-running operation. If you wanted to do it in a synchronous fashion, you just omit that async callback. Okay, so if you omit that, you will simply get a double back. Okay, whatever your bank balance is as a double object, and you're done. It's as simple as that. If you want to make it async, there's two different ways of doing it. You could use Java util future, and the way you do that is simply using the builder paradigm, add the async callback. Okay, and what this will do is that now you'll receive the future object with the typed parameter as your return type. And then again, you can do all of the Java util future manipulations. So is done, get, cancel, all of that. You can still do all of that here. If you didn't want to do it, if you didn't want to use features, okay, you can also use callback as a style as well. So all you do there is you call async, and then in the get parameter, you pass in an invocation callback. Okay, and the invocation callback has two different methods, complete and failed. Okay, in case of complete, it's a successful execution of the background thread. In case of failed, there is some failure, in which case you'll receive a exception back that you need to handle. Okay, I'm actually going to skip over a WebSocket just for in the interest of time, so I can move on to something else. I'm sort of running short of time. Okay, Java EE concurrency utilities is actually a relatively important thing as well. So let's talk about this for a second. In Java EE, I said there is many different ways of handling asynchrony, right? You can handle asynchronous communication by doing EJB async, servlet async, JAX-RS async, JMS, and the like. So you have a lot of features available to you. However, in some cases, you may need to still use low-level threading APIs, okay, in Java SE land, so thread objects and runnable objects. So some examples of this is when you need fine-grained control, when you have specific workloads where you need to set the thread pool size, you need to set timeouts and the like. Or if you are a framework writer, okay, and you need to spawn your own threads, that's another case where you need to use low-level threads, Java SE style threads. Well, the problem with doing that in a Java EE environment is that those threads are not managed by the Java EE container. So inside of those threads, you are not going through the application server's thread pool. Those threads are not monitored or managed, meaning if you open up the, let's say the WebLogic console, you won't be able to see, okay, these are the threads that are running. If it's a long-running thread, you won't get automatic termination of that thread. You will not get any warnings that there's a long-running thread on your system. You will not know who the currently logged-in user is. You won't know what the class loader context is and the like, because all of that information is simply lost because you're suddenly in the JVM level rather than at the application server level. So what is the solution to this problem? Well, the solution to this problem is using the new Java EE7 concurrency utilities, okay? So when you're using this Java EE concurrency utilities, instead of creating your new thread object yourself in Java SE, what you do is that you submit a runnable, okay, to an executor service managed by the container. Okay, so take a look at this code for a second. I am injecting the executor service, okay? When I'm injecting the executor service, I can then create a new thread, okay, by saying executor.execute, okay? And this will actually spawn a new thread behind the scenes for me, okay? It's as simple as that. And there is other facilities that come with the Java EE concurrency utilities besides this. Okay, so you can create scheduled threads, you can create thread factories, you can create your own custom thread pools and the like. So a lot of low-level facilities that you would otherwise use in Java SE only in a managed, reliable fashion. And again, this thread is going through the app server's thread pool. It is secure, transactional, all of that stuff. Okay. I will not have much time left to talk about Java SE concurrency utilities, although perhaps maybe I can ask permission. It's the last session of the day. May I have 5-10 minutes? Thank you very much. I really appreciate that. Okay, hopefully you don't mind. Okay, another 5-10 minutes of your time. Okay, so Java SE completable features are very, very important. It's best to explain this in terms of code. Okay, so I will try to do that and explain to you why this is important and why it is relevant for doing reactive programming. All right. So in order to understand this, let's start with a very, very simple bit of code. All right. So just take a moment to take a look at this code. It's relatively simple. What we are doing here is calculating underwriting. Okay, so we are calculating how much coverage you can give to an insured person. Okay, so in order to do that, there's several steps that we need to do. We need to get the assets. We need to get the liabilities. We are going to calculate the credit score of the individual based on the assets and the liabilities. We're going to get a health history. And then from the health history, we will calculate a health score. And then finally, we invoke the underwrite method to calculate the final coverage that you get. Okay? This code looks harmless, but this code can kill your system. Okay? Why is that? The reason this code can kill your system is because all of these calls, get assets, get liabilities, calculate credit score, get health history, calculate health history, and underwrite. These can all either be I/O intensive tasks, which means you are calling out to perhaps external systems, okay, to get your asset information, to get your health history, okay? And it may also be CPU intensive, okay, because things like underwrite and things like calculate credit score may be doing a lot of complex mathematical calculations, okay, which will take up CPU on your machine. So if you try to run this code as is, because this is running in a sequential fashion, okay, each of these calls will have to wait for the previous one to finish, which means this code will become a bottleneck in your system. These threads will hang for a long time before you finish executing this bit of code. So is there a solution to this? The answer is yes. Okay. So how can you solve this problem? You can solve this problem by doing those lengthy operations on separate threads. Okay, so this way, this synchronous blocking code is now becoming asynchronous parallel code. Okay, so you're going to do get assets on a separate thread, then you're going to do get liabilities on a separate thread. You're going to calculate the credit score on a separate thread. Okay, so these are all parallel threads of execution, which means that you're solving the problem of doing CPU and IO-bound tasks in a sequential fashion. Okay? There are two problems with this code. All right? This code is good, not as good as it could be. Number one, this code is a lot more complex than this. Yes? Number two, this method is actually prematurely blocking. Okay? Because notice that f1.get and f2.get calls. Okay, if you know the Java util future API, those are blocking calls, which means that code will block until both f1 and f2 are done. Well, guess what? That means that you cannot proceed and do these other things, okay, other things in parallel, which means in reality you have the illusion of parallelism, but you actually do not. You're not achieving the full levels of parallelism that you could, all right, with this code. Is there a solution to this? Yes. One solution is not using Java util future, but using callbacks instead, okay? And when you do that, you will have a nice introduction to something called callback hell, okay? And I won't show you this code. I'll let you take a look at this code on your own time, and you'll figure out very quickly why this is called callback hell. Okay, it makes this code seem nice, all right, as scary as that may be. So is there another solution to this problem? And the answer is that, in fact, yes, there is another solution to this problem. It is called Java SE8 completable features. To understand the difference between Java util future and completable future, let's take a look at this code. So this is processing the payment. You've seen this code before, right? In this case, instead of returning a Java util future, we are returning a completable future instead, all right? We're executing this thread using the Java, using the executor service, the managed executor service in Java E7. The difference is that when we are done, we are saying, instead of returning a future object, okay, we're actually saying future.complete. Okay, so you're making a callback, all right, using the completable future handle. The other thing you should notice is that the actual handle, completable future, is returned for you, okay, before this thread of execution even happens. All right. Now notice what happens on the client side. All right. So on the client side, there is no get method invocation, is there? No. There's no blocking code. None of this is blocking code, in fact, because what you do here is that you register a callback. Okay. The then accept call simply allows you to register a callback to say, hey, when this completable feature completes, when I get the process payment method done, please do this. All right, so this is not a blocking code at all. This is all non-blocking code. Beyond this, Java util feature does a lot more than just to allow you to do non-blocking callbacks. It also allows for composition, all right, which means you can take a completable feature and combine it with another one. All right, so take a look at this code for a second. what we are doing here is we've rewritten this code such that there is no blocking points whatsoever, okay? So we're doing get liabilities, doing get assets, combining those two, okay, waiting for them, combining those two and registering a callback, okay? So what that means is when those two things are done, okay, then do this, all right? Namely, do the calculate credit score after you receive those two callbacks. And then, without waiting for that to finish, we're immediately calling the rest of the callback APIs again, and so on and so forth. So in fact, this code is completely non-blocking code, and it doesn't have the same problems as we did here. All right, it is not prematurely blocking. However, at the end of the day, this is not that simple to understand. All right, so that is in the end the lesson that I want you to learn here is this: yes, you can do reactive programming very, very effectively using Java EE and Java SE8. There's a lot of features in Java EE that will allow you to do that. There's features like lambdas that you saw, completable features that you saw that also will help you out in designing very nice reactive systems. And so will the Java EE runtimes, because they handle all of those other external concerns that you don't need to worry about. However, do be careful. Okay, and the features that I showed you today are actually some of the most advanced features in Java EE. So this is the realm that you're entering when you buy into reactive programming. Okay, so there's some features for you. Please take feel free to take a look at them, and that's it. Thank you for staying. Arigato gozaimasu, and also thank you for the additional time.